Okay, in 4.4, we're going to talk about a concept called conditional probability and independence. The probability of an event can change if we know that some other event has occurred. The probability that one event happens, given that another event has happened, is called conditional probability. The conditional probability that event B happens, given that A has happened, is denoted by P with B bar A. Now, this last letter right here, that's the given one. And it does matter in the way you process the problem, okay? So it's B given A. When you read it, you don't say the bar, you say given. Probability of B given A is how you would read that correctly. All right. By exploring probabilities through a two-way table, we can determine a general formula for computing conditional probabilities. All right. And really, you don't have to worry too much about this, but I do want you to write this part down in your notes, okay? And it would be good if you wrote all of this right here. It's the probability of the intersection of A and B, meaning that both events occur, divided by the probability of the given, okay? Whatever part is given, given that one event occurs, all right? So it's a little different if you're using a two-way table or a Venn diagram, so we'll practice that. Now, suppose you want to toss up your coin twice. You define the events. A, the first toss is ahead. B, the second toss is ahead. Okay, we know that the probability of A is 1/2, probability of B is 1/2. Okay, now what's the probability that you get B given A? The second toss is ahead, given that the first toss is ahead. Okay, this is a conditional probability that the second toss is ahead, given the first toss is ahead. The coin has no memory, so it's still the same, 1 out of 2. It doesn't change. Now, what's the probability that you get the second toss is ahead, given the first toss is not ahead? It's tail, right? It's a conditional probability that the second toss is ahead, given that the first toss was not ahead. Getting a tail on the first toss does not change the probability of getting ahead on the second toss. So the probability is also 1 out of 2. And here's the key thing I want you to catch, is that getting a tail on the first toss does not change the probability of getting ahead. Okay? This idea right here, that the event of one does not change the probability of the event of the other, that is the idea of independence. So we're going to really work on that in this section. In this case, the probability that B given A is equal to the probability of B. Knowing whether or not the first toss was ahead does not change the probability that the second toss was. Okay? We call these two independent events. They don't affect one another. Okay? Same thing if I roll 2 die. When one ends up does not affect the other. Okay? Same idea. Now, you have to be able to find this mathematically. It says A and B are independent events if knowing whether or not one event has occurred does not change the probability that the other event will occur. In other words, events A and B are independent if you can show the probability of A given B is the same as the probability of B. All right? So other examples of independent events. Landing ahead after tossing a coin and rolling a 5 on a single six-sided die. Or choosing a marble from a jar and landing on heads after tossing a coin. Those two things don't affect one another. Or rolling a 4 on a single-sided die and then rolling a 1 on a second die. All of these are independent events. The outcomes do not affect one another. And we're going to do a practice problem where you have to show it mathematically. All right, let's do this with a table first. Finger length and gender. Is there a relationship between gender and relative finger length? To find out, we randomly selected U.S. high school students who completed a survey. The two-way table summarizes the relationship between the gender and which finger was longer on the left hand, index or ring finger. All right, suppose we randomly select one of the survey respondents. We define events R as ring finger is longer and F is female. All right. So it says find the probability that R given F, that ring finger is longer given they're female. Now, when you're using a two-way table, what you need to do is recognize which one is given. And the female part is the given part, right? And so you take that and you focus only on that column of the table. We're only going to use this column because this is the given part of the table. That's all we care about right now. Now, from that, we can calculate our probability really easily because R means the ring finger is longer. So it's going to be just this 82, right, out of 212. So it's 82 out of 212, and as a decimal, that's 0.387. Now the problem also says to interpret, so we have to interpret that. So I'm going to scooch over where I have a little more room, and it would say this: given that the person is female, there is a 38.7% chance, or you could say 0.387, it doesn't matter, chance that her ring finger is longer. B, given that the chosen student does not have a longer ring finger, what's the probability that this person is male? Write your answer as a probability statement using correct symbols for the event. So I'm going to erase the markings I put on my table so we can go from a clean slate. Now, let's put this in correct notation. The probability that this person is male, given that the chosen student does not have a longer ring finger. The ring finger is not longer, so we put the complement. That's the given part. And what's the probability this person is male? So it's not female. Okay? So now think about this. If they're not female, or I'm looking at the ring finger is not longer part, right? So I'm going to use two parts right here. This and this. Okay? And they're not female, meaning they're male. So I really just want the male part. Okay? Now, what do I do with that? Well, I just add them up. So I do 45 plus 43 over their totals, which is 123 plus 95. Okay, and that gives me 88 over 218, which is 0.404. Okay, so always start with what's given and then isolate what it is they're looking for. Okay. Now let's try this with a Venn diagram. Okay, we've kind of done this problem before, but this one is going to ask for a conditional probability. The National Center for Health Statistics conducted a survey of phone usage in a random sample of U.S. households in December 2012. Each household was identified as having a landline, telephone or not, and having a cell phone or not. Define event L as having a landline, and event C as having a cell phone. The Venn diagram just summarizes the data based on these two events. Okay. Now, question is, what is the probability that a randomly selected household with a landline also has a cell phone? Now, the given is this first statement here, the landline. Given they have a landline, also has a cell phone. So even though they don't use the word given, this is conditional because it has also. All right. So in the notation, I would say the probability that a cell phone, given, a landline. Now the formula you wrote down says the probability of C and landline. So it's the intersection over the probability of the second letter, which happens to be L. Now, what is the intersection? The intersection is where they overlap, right? So this is 0.51 over the probability of landline. Now, landline is this whole circle. So 0.9 plus 0.51 is 0.60. So when I divide that, I get 0.85. All right? So pay attention to the wording to get everything in the correct order. Example 3. The students in Mr. Tabor's statistics class completed a brief survey. One of the questions asked whether each student was left-handed or right-handed. The two-way table summarizes the class data. Choose a student from the class at random. Okay? Then it asks me, are the events female and right-handed independent? Justify your answer. So remember we said, so to show my independence, I've got to show that the probability of being right-handed, given that they're female, is the same as the probability that they're right-handed, given that they're male. Right? That's what I got to do. It's the male is the complement of female, right? So I could have said F with the C on it. Okay? I've got to show that these two things are the same. So using my table here, I can easily find that. So given female, I need some totals, so I'm just going to add these up. 21, 7, 4, 4. Okay? So right-handed and female goes on top, right? And then probability female. Okay. So right-handed and female, that is 18. Probability of being female was 21, right? Okay. Well, that gives me a 0.857. So let's see what happens when I do the same process, the probability of right-handed and male over the probability of male. Right-handed and male, there's only 6 of them, and probability of being male is out of 7. Well, that's also 0.857. So because these two probabilities are the same, the events female and right-handed are independent. So I write that out because they are equal. The event right-handed and female are independent. Okay? So what did I do? I looked at the given statements, one with the original and one with the complement. I look at the two probabilities. Okay? We'll try some more of this in class.